Good morning, everybody. It's it's time for us to be short-winded or long-winded or whatever. So if we can start it up. Okay, so today I'm going to tell you about windmills and sailboats because that's more fun than E equals I squared R and pi R2 and all that good stuff. So this is just a little introduction to use of solar energy and wind energy. And like I mentioned last week, my dad built a T like that out of 4-inch iron pipe welded together. And that's where my mother would hang the clothes. I was fortunately not tall enough to reach the clothesline at that time, so I didn't have to hang. I could take them off by just janking them. So last week, Alan Colehouse, who lives out in the outback, told us about his house. And I had mentioned the University of Delaware house of solar energy where they had heating on the roof and all of this. This is Alan's house and Lynn Ryan's house up in Ohio. And he has solar collectors on the roof and a 3,000-gallon insulated tank in the basement to provide the heating for the house. And while we were talking last week, he got on the internet and told me that the temperature in the house was 58. So he knew that the emergency heating had kicked on while he was down here in Florida. So they are still in use. Battery storage update. John Paul gave me a link and I was able to look up and we'll see it. Florida Power and Light is doing a lot of solar power around the state of Florida, and the company that's the owner of Florida Power and Light is also doing work around the country and maybe overseas as well. So this is in Parrish, Florida, Manatee Solar Energy Center. It's 409 megawatts and 900 megawatt hours. So it'll provide power for about 2 hours when everything else is off. And we've seen that you need to have some base load capability because if the wind stops and the sun stops, then those two energy sources are just sitting there looking at you. It's the size of about 30 football fields, charging capacity of about 100 million iPhone batteries. And this is what one of the units looks like. So the device down here, which you can't see, and is one of the battery packs that goes in there. So they have started doing this around in Florida, and it will become more popular and maybe even less expensive as they do more and more of it and the manufacturing picks up. So the Wynwood Miami storage facility will do 7,000 homes for 4 hours, and that's what it looks like, a big building right in the energy complex where they have the transmission lines and the transformers. So that was an update from last week of battery storage. So what we're going to do today, we're going to talk about the source of wind power, and we'll look at historical uses of wind power, and there's some very interesting stuff. Sailboat designs, windmill designs, then we'll get to electric windmill designs, and energy storage. I just showed you that already, and we'll talk about some other kinds of energy storage possibilities. The future of wind power and the pros and cons. So where does the wind power come from? The first day I told you that nearly all of our energy really comes from the sun because the sun provides us with the solar power, and we're going to see that it also provides us with the wind. So the daily wind is caused by uneven heating of the Earth's surface. So the sun will heat up the land and it will then draw in air from the water. And you can see this frequently in the summertime in Florida. In the really bad thunderstorm days, you will see a band of thunderstorms that come from South Georgia all the way down to the Everglades when the winds from the Gulf come in and collide with the winds from the Atlantic somewhere over the land. And it's a pretty spectacular display of radar when you see that. The global winds, the land closer to the equator, of course, is warmer than everywhere else. So you'll have the winds will be driven by the solar heat on the ocean, and near the equator, you'll see the trade winds that are blowing come in from the east. And they have these things called Hadley cells where there's some rotation of the wind cycle going up into the higher latitudes. And we've seen that the polar cell can come down to Florida yesterday and the day before. So the sun is really forcing all of these wind conditions. And the westerlies north of Florida and the Gulf Stream, as Benjamin Franklin discovered and told us about, will blow toward the west, and it helps the old guys with their little sailboats that mostly go before the wind. They can get south and then come across to the Caribbean. And if they're ready to go back, they go with the Gulf Stream up north and then pick up the westerlies and go back to Europe with their gold and silver. But that's a different story. So the trade winds are caused by the Coriolis effect, and they're between 5 and 30 degrees north and south of the equator. The doldrums are the latitudes between 0 and 5, and you've heard about the old sailors getting stuck in the doldrums and water everywhere, nor any drop to drink. Those are in the area near the equator where the winds aren't really very helpful for the sailors. So people have been using wind energy for thousands of years, and people have been separating grain from chaff for thousands of years. Just lift it up, let the wind blow away the chaff, and collect the grain in the basket. People have used wind energy to propel boats along the Nile River as early as 5000 BC. They were called feluccas, and this is what they look like. And you will still see them. Anybody here been to Egypt? Did you see the feluccas? No? Yes. Yes. So they're still in use. It's a very simple boat, simple sail, and it'll go on the river. The river flows north. So if you want to go south, you need a different way to go. And the sailboats turned out to be very good for that. Other sailboats through the ages. These are the Nina, the Pinta, and the Santa Maria that came with Columbus when he so-called discovered the Americas. And you can see there's different kinds of sailboats there. The one on the far left has some sails rigged kind of like the felucca, so they can go into the wind a little bit or with the wind on the beam, which is like perpendicular to the axis. The other guys have big sails fore and aft, and they really need wind behind them to make much progress. And it's quite a bit of an effort to bring one of those boats around to go in a slightly different direction, and going into the wind is never very good. This is a French man of war, and you can see their cannons bristling all along the sides. And they've been at war with England approximately too much, because you see all the cannonball holes in their sails. And these guys also weren't very maneuverable. And they used to have their sailboat wars were in a line of ships, a straight line. And so this was called a ship of the line. And we'll see another guy. This is HMS Victory, the ship that Admiral Horatio Lord Nelson was on, the flagship. It's still in commission in Portsmouth, England. I went through it in 1956 when I was on a battleship for my first cruise from the Naval Academy. And he was a short man, which is very good because those decks are not very far apart. And he died on the HMS Victory. He won the battle, but he died there, and there's a memorial in the area where he died. The ship is in dry dock now and not floating. This one is up in Boston, the oldest Navy ship in commission. Currently, the commanding officer is a female for the first time ever. Old Ironsides, and it was made out of really thick oak, and supposedly the cannonballs from the British just bounced off the side, and the British gave her the name Old Ironsides. This is more like a ship that you would see. Many of the academies around the world, naval academies, have a tall ship as one of their ships. And the Coast Guard Academy still maintains the Eagle, which is a tall ship, and all of the cadets have to climb up the rigging. Those sails have to be set by someone up on those cross arms, and there are lines that pull up the sails that are on the forward part of the ship. But I never went on one that size, and I never had to climb the rat lines and get up into the yard arms there. They're furled up, and you can see, well, you can't see the laser, but right along in here, you can see those are reef points. They're little pieces of line, sort of like clothesline. You can pull the sail up and tie the reef points off to the yard arm if there's too much wind. And you can pull it all the way up and secure it to the yard arms and put all the sails down. When I was in Oslo on that same cruise, the Norwegian Naval Academy had a beautiful, fully rigged, tall sailboat like this. I don't know which one this is. Okay, the wind energy. 200 BC, simple wind-powered water pumps were used in China. And this is a drawing of what that might be. You can see down in the water, down here where you can't see the laser, but in the lower right of the corner, that is a ladder kind of an arrangement, and the sail rotates, and then it rotates the ladder, and so it just kind of scoops water up and splashes it slightly higher. It can only raise it a foot or so, but that's enough to put it into a big pen for making salt by just normal evaporation. This is another one. There's still some in use in some of the islands off the coast of Africa to put the seawater into their salt pins. So windmills, now these are really cool. The windmills were woven reed blades. They're really strange looking things, and we'll have a look at them, but they were in about 1,000 years ago in northern Iran. This is what they look like, and it's in an area where they have wind coming off of the Caucasus and what do they call the Great Plains, in Russia. But anyway, the wind frequently blows this way. They built these things so that they will catch the wind. And this is what a cross section looks like. So down below, you have a shaft coming down as a vertical shaft turns the millstones. You can pour the grain in and you can grind the grain. And they've been doing that for about 1,000 years. This is a different device that they had. It's a wind catcher. And the blue is the wind blowing through the tower down into the building and circulating around. And if they had an area and near the water, they could get some lower pressure from the wind blowing, and the water could help cool the air and cool the building, and then it would blow out the other side of the tower. Okay, now here we are. I have my helper just in time. This is a video and it has some sound. You ready?
Some of the oldest windmills in the world can be found on the gusty border of northern Iran and Afghanistan. Nashtafan is a city located in the Khorasan province of Iran. The city name was previously Nishtufan, translating to storm sting, which is appropriate for this windy city. A 65-foot wall blocks the intense gale force winds, and atop of that wall are around 24 vertical axis windmills. They are made from clay, straw, and wood, and it's estimated that they were constructed over 1,000 years ago. The windmills still function today and can be used to mill grain into flour. In 2002, Nashtafan was recognized as a National Heritage Site by Iran's Cultural Heritage Department, in the hopes that it will be around for thousands of years to come.
So that was a cool set of windmills that I didn't know anything about until Mr. Google helped me look for windmills. Okay, if we can skip out of here. You may have to escape. Okay. So that was the windmills in Central Asia. Now we're going to talk about the Spanish windmills. La Mancha. Everybody's heard of Don Quixote de la Mancha. La Mancha is a region of Spain in the central Spain area. And if you haven't had it, someday you should try Manchego cheese, which comes from La Mancha, which is a very good cheese. So they had the windmills. If I'm pushing the right button, these are what the windmills look like in La Mancha. And this is what Don Quixote looked like. And apparently he didn't see the sign. Now we get to the Dutch windmills. The Dutch are famous for their windmills, and they had their windmills because most all of their land, or a huge fraction of it, is underwater. And the windmills were built to pump the water out into the ocean and dry the land off for irrigation, farming, and everything else. They also had a lot of sailboats. The Dutch were very powerful traders, and they had competition between the Dutch and the French and the Spanish and the English back in the early days of sailboat travel. And finally, the Dutch kind of lost out in their powerful navy, got beat by the French and the English, and all those countries would team up one time or another with each other to knock another one down, and the English ended up mostly ahead. These are the Dutch windmills that you can see today, and they're really very interesting, and many of them are still in operation, and people live in them, and they get free rent if they live there, and they're required to run the windmill a certain number of hours per day or week for tourism, and they still work. You can see on the one on the left, the water inlet is here. So this is a windmill that would be pumping water across and out to the ocean. This was a tour group that Carol and I were on quite a few years ago, and we went to the windmills, and our tour guide is standing there with his hand on that wheel. You can see that if you look in the background, the windmills are pointed in various directions, and that chain is wrapped around and like a windlass, and you can use that big wheel to turn the windmill so that it faces the appropriate direction to catch the wind. And the one windmill that we went into, I looked all over for my pictures. I did not find it, but it was actually making peanut oil. And I'll show you some gears, but what it had was a gear with some cogs, and it would raise an arm up, and the arm was about this square, just wood, and they would put a bag of peanuts down below, and the arm would come down and whack it like a forge every few seconds or every few minutes or so. And there was a break that the operator could stop the thing and take the crushed peanuts out and put them in another place. They would use that for fodder, put a new bag in, and it would go start slamming the peanuts again. And he would have peanut oil being caught in a container down below. So this is what a windmill looks like. You can see at the upper left there is where the vanes of the windmill would be that turn the mechanism. And you see in the top, there's a vertical wheel that has cogs on it, and that engages with the horizontal wheel below to turn the shaft that goes all the way down, and it reverses the process. There's the little wheel with vertical slats in it that are like dowels, and there's a cog wheel in the bottom, and it turns the whole pumping mechanism, in this case, just a water wheel, and it pumps that out. These are the kind of cogs. They're just a big wooden stake. And there's another, I don't know if we can see the other one where it has the vertical stakes, and this rotates around. So the window, the vanes themselves have sails on them. So you have to deploy the sails, and that's why you have to turn the top of the windmill around to catch the wind. And depending on how strong the wind is, you can furl this sail just like the sails on the ship to match the strength of the wind against the ability of the windmill to not run so fast that it blows apart. There was a great movie, I don't know, we've seen it a couple of times. It's called Foreign Correspondent. It's who's the guy? The fat guy that's always in the front of the movie. Hitchcock. It's a Hitchcock movie about World War II, and it features things at a windmill that happened. And so the windmill played a part in the movie. So it was a cool movie. Every time I see it, I wonder what's going to happen because I don't remember. I've seen a lot of movies more than once and keep thinking, how does this end? Okay, this is a totally different kind of a windmill. This was built in Cleveland, Ohio in 1888 by a guy who had more money than brains. This thing is in his backyard, and I guess they didn't have zoning requirements in those days in the Cleveland area, so he could build this thing. It's a 60-foot tower, 40 tons iron in the tower. Maybe he was a steel magnate. 144 blades, 60 feet by 20-foot sail. So this sail, like we'll see in some other things, uh, allows the whole tower top part where the windmill is to rotate around to catch the wind at the proper angle. This had a 500 RPM dynamo attached to it, 408 batteries in the basement, 12 kW peak. A normal house will use about 1,000 kW a month, more or less. And we all know what a kW is, a kilowatt of power. Your flat iron is running at about a kilowatt. So it's a flat, so this is 12 flat irons of power. Ran 3 motors and a lot of lights in his house. Oh dear, I do that frequently. Which button was that? This one, I think. Yes. It lasted 20 years and the batteries lasted 40 years. Farm windmills. We've all seen those as we drive around through the countryside. And this is a great picture because it caught the sun on the farm windmill. These were typically used to pump water at the very top where the vanes are. And you see its sail also pointing it in the right direction for the wind. There's a crank at the top. And as the windmill turns, the crank rotates around like the crankshaft on a car, and it raises and lowers the pump. So here's the pump being raised and lowered, and I have another picture of down below, but it was typically used to pump water up for the cattle without having to have a gasoline engine or anything else to do the pumping. So down below, you can see the pipe goes up and down. And have you ever used one of these hand crank water things to get water up? It's the same process. When you push the hand crank down, it pushes a little flapper down and catches the water and pulls it up and goes down. So it's kind of got a little check valve in it. But this is the sand with the water in it, and it has a strainer, and it pumps water up for the cows or the horses. This was a very interesting book. I don't know if any of you have seen it or heard about it. The Boy Who Harnessed the Wind. So this was in a village in Mali, the Wembe village near Kasunga, Mali. There was no electricity there, and it was a very small village and a very poor village, and it was on the outskirts of a town that was not also very well known to any of us. But he was a very curious boy, and they had a library, and he went to the library and he got books out and he read about windmills, and he noticed that the bicycle generator powers a headlight. And he thought, aha. So he scrounged parts from the junkyard, and this is a fan blade from a tractor that he got from the junkyard, and then he attached big vanes to it to catch the wind. He built a tower to hold the bike, the fan blades, the generator, the chains, and the wires. And he built all of the stuff inside the house, the circuit breaker, which was, I don't know how he did that. And it's probably just pull a plug and it'll stop. This is what the thing looked like. It's a shaky looking tower with the bicycle up on top and the big wind vanes. And everybody thought he was crazy until he turned the lights on in his house. And so he built another windmill to power the water pump because they didn't have a water pump for the village. So a local partial solution to drought for his village. And the book makes very interesting reading. He gave a TED talk about this project, and he got, I think it was a scholarship to Harvard. somewhere. He became sort of famous for having done that. Okay, this one is another video. This shows you the danger of windmills, the big windmills you see there. So that's how dangerous these windmills can be. Okay, if we can sneak on out of there. Oops. Okay, this is pouring the foundation for one of those big windmills. Look at all of the reinforced iron down below and the amount of concrete, because those windmills are really big. They're tall and they have a lot of force against it. So it needs to have a super duper foundation. And this is just the one of the ones that was being poured. So when we left Copenhagen on a cruise one time, I took this picture out my balcony window of the wind farm that's in the ocean right there out of Copenhagen. Um, and I thought it was really cool. This is what one of those windmill generators really looks like. And so it's very complicated. We'll look inside one of them, but they have these big vanes and it has pitch control, just like the props on an airplane, so that you can adjust the pitch for the right amount of wind that you're getting. It has a yaw control, so you can point the windmill in the direction of the wind. It has a clutch in it, and it has a brake so that you can stop the windmill if you have a problem. So this is the insides, and we don't need to go through it very much, but you can see the complexity of what's in that nacelle up in the top. So you have a high-speed rotor and a low-speed rotor. The windmill turns at about 10 to 20 revolutions per minute. We saw the girl jumping the shadow there, and that's about the speed that those things turn. And you wonder how it can make any electricity turning that slowly. There's a high-speed thing, but it's got a lot of other auxiliary equipment in there. Hydraulic unit for controlling pitch and yaw. It has the gearbox to run the generator at the speed it needs to run. It has cooling system and a lot more stuff inside. It's a very complicated piece of engineering. So these guys thought maybe power lines would be better than trying to sit on the rotating blades. How tall are the wind turbines? They're really big. Here's the Empire State Building, 1,400 feet high, Eiffel Tower, about 1,000 feet, Statue of Liberty, 305. The average onshore US turbine is 466 feet high. So with the blades, it's taller than the Statue of Liberty. The tallest onshore turbine is like 574 feet. The new GE is 853 feet high, and the Block Island offshore wind projects are 590 feet high. So these guys are pretty massive. This is one that was about the Norwegian towers, the Oslo Radhaus and whatever the other building is there, the plaza shows you this now is a floating offshore wind turbine. So it's in 90 meters of water, and then it sticks above the surface of the water another 100 and some odd meters, and the blade's diameter is 157 meters. So this is a huge thing, and it's anchored, it floats on that empty cylinder. That's what holds it in place. And then what holds the cylinder in place are some cables that are attached to the seafloor. This is a turbine blade of one of the GE windmills that is an offshore project. You can see from the size of the min that the diameter of that hole is about 20 feet or more, and that's how it would be connected to the nacelle of the wind generator complex that's on top of the tower. And the thing is several hundred feet long. And I don't know how you do anything with these guys when it's that big. As an engineer, it's a project that I'm not sure I'd want to be involved with. Okay, here's another little video. This is an oopsie kind of a video. And we don't need the sound because it's in duct or something. But you can see the blade struck the upright and the whole thing disintegrated and landed, hopefully not on anyone. And it'll go through with some slow motion to show you what's happening. You can see the blade hitting the tower, and then that destroys the entire device. So that's why it's important that you have all that mechanism up in the nacelle to keep the blades out away from the tower support structure. So that's all we need to see of that one. Thank you. So the turbine power is typically around 4 megawatts of power from a wind turbine. Average power load is 40 to 50%, and I've showed you before, and we'll see again, the power capacity of a lot of different things. The wind. Oh, sorry about that. I'm sitting back too far. Yeah. So average load is 40 or 50%. Sometimes the wind is too strong and you have to shut the thing down and put it in a safe mode. Sometimes the wind is not enough to rotate the vanes. So they're guessing 40, 50, maybe 60%. The turbine cost is about $4 to $6 million. So it's about $1 million per megawatt or a dollar per watt. That's a big investment on a complex machine. Time to pay off the initial cost is maybe 7 years, kind of like our solar panels here at Oak Hammock. And they hope that it'll last maybe 25 years if none of the blades hit the upright. And typical household is about 1,000 kilowatt hours per month. Okay, this is the 6 megawatt GE structure. 6 megawatts out. Rotor diameter is 150 meters, which is like 450 feet. Hub height is 100 meters, which is like 300 feet. And it has direct drive permanent magnet. And the rotor swept area is 17,860 square meters. And if you really want to get involved, you can calculate through the density of the air and the air speed and the volume swept and efficiency and all of that, and you can figure out what it'll be capable of doing. I didn't bother to do that. This shows you 3 of those GE power generating windmills offshore. And they are, you can tell by looking at the structures here, they are permanently mounted to the bottom. So they're in reasonably shallow water, meaning 100 meters or so. Okay, this is the inside of that. And again, you've got all that complicated machinery with brakes and yaw and pitch control and all that. But what I want to show you is right up here in the upper right corner, which the laser doesn't show very well. See the red thing there? That is a helicopter landing pad. So this tells you how big this dude is. And there's no other way to get people out there to service it if it needs servicing. This is a bigger one, 14 megawatts. And there's the statistics for it. So it claims to have a 61% capacity factor and 38,000 square meters swept area. It's a big, big thing. This is how you mount these offshore windmills. The one on the far left is mounted directly with its canister onto the ground to some sort of a foundation. The next one to the right is bottom mounted, but it has like a scaffolding that's mounted onto a foundation stuck on the bottom, lifting it up so it'll be at the appropriate height. And the other three are tethered, and they have three different designs. The one in the middle is got three canisters that will allow it to float. The one next to that on the right has a single canister, but again, three or more mounts to the bottom with cables to hold it in place. And then there's the one on the far right, which has three little flotation devices plus the canister. This shows you what these guys look like. You can see there's the ship over here, and that the ship is probably maybe 30 feet high. And so these guys are really enormous. Because they're floating in the seawater, you have to know if it's actually going to float and stay where you want it and not fall over. This is a wave generating tank. And at the far end, you can see some yellow, and you can see the blade right here, the blade. So this is a model of one of the offshore mounted wind generating turbines. And you can see these devices down in the bottom of the screen are hydraulically operated wave generating devices. So you can make any kind of waves you want to test the stability of this model. And then if your model design is good and the ocean waves behave like they do in this pool, you'll be okay. I've seen one of these pools, David Taylor Model Basin near Washington, D.C., as a pool for testing ship designs, submarine designs, and other designs. This is one of the towers, just another tower out there, but you can see the three yellow flotation devices. This is the Norwegian set of tethered wind generators, and they are not used to bring power ashore. They bring them near one of their offshore oil and gas platforms in the North Sea to provide the power for the platform, so they don't have to run a generator or bring fuel out, that sort of a thing. And it's in a very high wind area, so I don't know what their power factor is, but they must have some emergency power on the oil and gas platforms. So some innovative new designs. This is a company, these are 1 kilowatt. This is a company that makes these little guys that are capable of running your house. So it's a 1 kW if you put in some batteries. And I keep getting emails from them, but once you sign up on somebody's web page, they're going to try to sell you one of these. And the 1 kW units cost on the order of $1,500 to $2,500 installed. And you can see the skinny little mast, so it can be attached to the side of your house and lifted up over the roof line. So this is another one that's a vertical shaft, and the good deal about the vertical shaft is that it doesn't care what direction the wind is coming from. And next week, we'll see that also in some of the offshore ocean current power generating devices. You can't control where the current is coming from, so you best have one that will take the power from anywhere. And this one is from a company, and this doesn't run. So uh, it ran on the internet, but I couldn't get it to run on the thing. But you don't need to see it. What happens is it's mounted on light poles adjacent to the highway. And traffic going by, you know the wind generated. If you've been behind a big semi, you know there's a lot of wind. We push a lot of wind in our cars, and it spins these vertical axis turbines, and it provides power to the street lights that are on top of the masts. And it can, if there's enough power left over, they can put it out also to the grid. So there's the 311 on the right is what that one looks like. And this is a different omnidirectional on the side of somebody's house, a generator. And that one, you don't care where the wind is coming from, because no matter where it comes from, it's going to go in the right direction on that turbine. The ones on the left, I suspect, have some kind of a control to turn them around and catch the wind, but I'm not sure. This was my favorite wind turbine. It's a wind turbine on top of a sailboat, and we saw those all over the Caribbean when we went sailing with our son and daughter-in-law several years ago. And you can hear them, they whir a little bit. You can hear a little bit of noise while they're running. When you're sailing, generally they're not being operated. But when the boat is sitting there for months on end while the owner is not there, it will keep the battery charged, which means the bilge pump will be charged and be running, and the electricity is there if they need to have lights on it because of the anchor light. They have enough power to do that. And they're very small, and they just go a little bit. Okay, this is an electric vehicle truck with its own charging device, so it can go anywhere. I don't know how they move those things around. I mean, it's incredible. But yeah, keep going forever. Okay, let's just look at some of the costs. This is an array of all kinds of costs. The black arrows show us the offshore wind, the battery storage costs, and the onshore wind. And it's in, what do we got it in? Dollars per megawatt hour. So the onshore wind is cheaper because they're not as big. They don't have to be as ruggedly designed, and the installation is fairly simple. The battery storage is battery storage. The offshore wind, we saw how complex they are, and they're out in the ocean with salt water all around, saltwater spray. So it's not surprising that they cost more than anything. Okay, environmental considerations. Wind turbines can impact wildlife. There's a lot of stuff, I don't know statistics, but a lot of people who are against wind turbines talk about all the dead birds lying at the base of the turbines. I don't really know if that's true, but you have to have access roads to get to these. And we've seen them. Somebody here was talking earlier about seeing them in California. On the side of the low mountains in the Central Valley, you see all kinds of wind turbines, but you have to be able to get to them for access and for connections. We saw that the connecting to the grid can be a problem, and will be shown again through the rest of this series. They create noise pollution. airborne and underwater. There's complaints that the noise that these things will generate will kill the whales. So, save the whales. Don't put any windmill stuff offshore. There were two big projects scheduled offshore for New Jersey. They've been canceled because of all of the blowback from the people that don't want to see them, and the environmentalists say that it's going to kill the fish and the whales, and the fishermen are going to say, I'm liable to run into it at night when it's dark. So there are a lot of complaints and a lot of problems with trying to put wind turbines in. They say it's an undesirable site. I thought they were pretty cool when we left Copenhagen. They're out there in the salt flats. They're not really disturbing anybody, and they're providing a whole bunch of electricity basically free after you build it. Now, this one I thought was interesting. A lot of the location of wind turbines is in the Great Plains area in the far northwest of the country, north central even. And that's where also the IBM sites from the Air Force are located. The Minutemen and the other nuclear weapons are out there. And the Air Force has said that this is a hazard because if they get an emergency call from one of the sites, they got to come screaming in with helicopters at low altitude to solve whatever the problem is. And so the helicopter pilots are not too happy about running into one of these guys. So I thought that was an interesting complaint. The wind turbine speed, 10 to 20 RPM. The tip speed is up to 150 miles an hour for the large blades and maybe 100 miles an hour for the smaller ones. Saltwater corrosion in the offshore platforms. I don't remember if we saw in one of those close-ups of one of the platforms if we were seeing any saltwater corrosion, but those are typically steel or iron, and they're not really happy with salt water. Okay, affordability. The raw materials, steel. The major thing in these wind turbines is steel, concrete, fiberglass, resin, or plastic, iron or cast iron, copper, aluminum, and many of the components are recyclable. So there's not a question of what to do with the waste. If you take one of these things down, you can recycle a lot of it. The fiberglass and resin part, I think that big GE blade that we saw that was a couple of 100 feet long and about 20 feet in diameter was a combination of fiberglass, resin, plastic to make it light enough that somebody can pick it up and hook it up to that. I don't know how they're doing that. This locations of various sites of wind turbines in the green, and you can see they're in the Midwest and in the Southwest in Texas. In fact, Texas has a law that you have to first consider petroleum product power generation because they have all that oil underneath Texas. So they are less inclined to do renewable energy sources, but that's what saved them, as I mentioned, probably the first time. When they had the big ice storm and the great freeze, I don't know how they made out this year, but Texas Energy is its own energy complex, surround the state of Texas with a wire and don't let anybody's other electrons come in. I think they've changed their mind about that. But they were saved in the year that Ted Cruz flew to Acapulco because it was too cold in Texas. They were saved by their solar power and their wind power because it was so cold that some of the components on the natural gas generators froze and they shut down. So build them where the wind is. They're in remote areas, on farms. They have to be located about several hundred meters from a dwelling for safety and for possibly noise. So they're on the prairies and the Great Plains, offshore wind farms. This shows you, there you can see the Texas energy complex. They like to isolate themselves. But these are sort of divisions of where the electric grid kind of doesn't go across the boundaries. It really does some. But here we have another grouping of where people are kind of connected together. So it's the Electric Reliability Council of Texas, ERCOT. Not so reliable all the time. So these were the grids. I've shown you this before, where the connections are in 2020 and where there's large capacity connections from the nuclear power plants in Miami up to Tampa, and other places across the country. This is what will be needed in 2035 with wind power and solar power, a lot more capacity. You can see how wide the connections are to go between places where there is wind power and where there's solar power and any other kind of other power, to get it connected together so that there's some reliability, so that if you have a problem, Carol and I were living in Ballston Spa, New York in '66 for the great power outage in the Northeast. Something happened, I think it was in Canada, but that tripped off a few power plants. And then if you drop a whole bunch of the capacity of a power grid, the other guys are going to try to provide it and they will drop off because they're trying to put out too much amperage for the wires and for the turbines and the generators. And so they just had a sequential dropping of power from in the Northeast down to, I don't know if it got down to New York City, I don't remember, but we had no power for a couple of days. I was assigned to the nuclear prototype at West Milton, Connecticut, and we had to shut down the nuclear plant there because there is a safety requirement that you must have two sources of outside power that are independent in order to run a nuclear power plant for safety reasons and for safe shutdown. We had the same thing happen on my submarine when I was XO. We were in the Med. We were practicing for a engineering inspection, and we went out in the Med and we were doing engineering drills and practicing. And one of the things that you have to do there is you have a simulated problem that you can't run the reactor, so you have to run your diesel generator. The diesel generators on all the submarines had a blower, a turbocharger, and we blew the bearings in our blower for the diesel engine. We had to come back alongside the tender, and we were not able to go to sea until that was repaired. It's a safety item. So you need a lot of this power to share, but it has to be shared in such a fashion you don't shut down the world with a big problem. All right, this is the storage thing that I've shown you before. The green line is the amount of power that the system can generate while it's chugging along. The red line is the power that you need. You can see until 6 o'clock in the morning. You don't need a lot of power. Everybody's got everything turned off. And when everybody wakes up and starts turning everything on in factories and so forth, you need more power than you're generating because it's above the green line. The blue line down below is a storage generated energy device, unnamed, not what it is, but just shows you that when you are on the far left, the red line is below the green line, you have extra power, you put it in storage. When the red line is above the green line, you need power and you take it out of storage. And when again the red line goes below the green line, you can add some more storage to your storage device, whatever it is. So wind farms are distributed over large areas. They produce AC, except for that one GE device that was a direct drive permanent magnet making direct current. But others are typically making alternating current. It has to be converted to some other energy in order to be stored. There are no AC batteries. If we had one of those, we'd be in great shape. Storage must have high energy density so that you don't have to have, like we saw in Manatee County, 3 football fields worth of batteries, but you can't get around that. Oh, I keep doing that. Sorry about that. So there's some concepts for geothermal storage that I'm going to show you, and they're kind of weird and bizarre, but we can look on the left. They have bedrock and they're pumping compressed air or hydroelectric power and into storage there, and you can bring it out of storage when you need it. The next one on the right is going into the layer of salt, the salt mines. You can put methane, hydrogen, or compressed air in there and retrieve it. They can have storage in the coal mines of methane and compressed air. So it goes along with different kinds of strange ideas, some of which are in use, some of which are still talking points. I'm not going to spend a lot of time on them. So again, here's some cost comparisons. Offshore wind and what its availability, 18 to 48%. And the battery storage, 8 to 42%. And onshore is 18 to 48. Offshore, you generally have more wind and blowing in different directions, so they can have a higher availability. But if you wanted to spend some time looking at all of this, you can sort of figure out where people might be going with what they're trying to develop for the future. So we've seen this before, the fossil fuel and gas peaking. We'll talk about that in 2 weeks when we get to petroleum, coal, and gas. Renewable sources, the solar panels, you can look at the steep decline in the cost over time and size of capacity, so that the solar panels are now running about what onshore wind turbines would do. Solar towers, like the offshore ones, are more expensive. We saw that nuclear power is becoming more expensive because of administration, environmental concerns, cost of materials, not in my backyard concerns. And geothermal is running down and it's getting a little cheaper. But you have to go where the geothermal is in order to build one. And we'll talk about that probably on the last week, because next week we have a lot of stuff to cover on water power. So this is again just another comparison of time versus cost versus whatever kind of energy you're looking at. And the availability, I put the line up there for nuclear power, and coal and natural gas are probably running at about the same availability, around 90%. So that can be the base load, and you can have other kinds of renewable energy or biomass or waste to energy, but you need some kind of constant power, because the stuff that is other than what you have for constant power has a variable amount of time that it's available for you. So here's one of the guys with a problem. Next week, we're going to talk about water power. It'll be a damn interesting talk, I hope. So, are there any questions? Boy, no questions. We can go home.
Hold on.
Oh, John.
Hold on.
It's not obvious to me why it seems like 3 blades is optimal for a wind turbine, because if you put more blades in, it seems like you're getting more, you would get more of the wind that's racing through. It's not hitting a blade. That's obviously wrong, but do you know why?
Now, I don't know why, but remember the first guy that had that 60-foot tower, he had 100 and some odd blades on his wind turbine, and he was getting something like 20 kW out of it. So I don't know why that is, but they all seem to be only 3 blades. And it may be just a mechanical engineering connection to the nacelle, because those blade connections, we saw that 20-foot one hook up. There may not be much room on the nacelle to add another blade. That's a guess.
I wonder, John, if it's diminishing returns. Yeah, more blades and you get more energy, but cost-wise, the cost goes up too faster than the energy you get back. One of the things I have seen is that the wind turbines, yes, there's been problem with killing birds. And I've heard that if one of the blades, either one or two, but even if one blade is painted black, it decreases the bird deaths by a big number, like
I saw that
50%.
somewhere, and
And
I'm not sure why that would be. Maybe they can, I don't know. Maybe if you can't see them, you can't run into them.
I think Ellen had put a couple links about whales and bird mortality, but. I don't
Yeah.
know. Mhm.
So there are concerns. The not in my backyard concern is for everything that you want to build that might be efficient and useful, but nobody wants to be able to look at it or have it nearby. And 3 Mile Island was a disaster that could have been avoided if the operators died. And we'll probably talk about that in the last session. But the safety situation on the 3 Mile Island power plant would have taken care of itself. And there were some problems that the operators caused that caused the whole thing to happen. But the not following procedures, and after that, all the commercial power plants had the INPO, the Institute of Nuclear Power Operations in Atlanta, and it was run by a bunch of submarine Rickover trained nuclear power operators who instituted those kind of operating procedures and safety precautions in all the operating nuclear power plants. So Will has a question.
I wanted to go back to birds for a minute. The blades don't go around that fast. So if the birds are, 40 feet from the hub, they can see the blades and beat them. But the tips are going at 150 miles per hour. And I don't know a bird that flies 150 miles per hour. So if the birds are out near the edge of the blade sweep area, they're goners.
Yeah.
If they avoid that area, they're all right. But who knows?
And I wonder if there are more bird deaths in the migrating nighttime birds. A lot of them fly at night. So maybe they need to put lights on the blade or something. I don't know the answer to that. Anything else? Nobody on Zoom had a question?
Oh, wait, what's the status of solar panel manufacturing in the US? Are most solar panels still manufactured?
Most solar panels are still manufactured overseas, but there was a pile of money that was in one of the recent bills that Congress put through for renewable energy, and they're trying to build solar panel plants. Where was it? Ohio, somewhere up north, probably where they needed some votes. So you could put a factory there and say, what a good guy I am. but there's the only reason they're built somewhere else is because cheap labor somewhere else. The availability of the materials to make the solar panels is pretty much available anywhere with the transportation system that we have, with all of those huge ships with all the cargo containers on them. You can get your stuff if the Panama Canal is open and if the Suez Canal is open, but it can be built anywhere. So whatever they're going to try to do here, I suspect will be highly automated, and we'll see. It won't happen for a couple of years. Vietnam, Malaysia, China, where else are they making them? No, in the Far East where labor is cheap and where a lot of the materials are. China has a lot of the materials because it has a huge country with a lot of mountains and other kinds of various topography, where the materials that go into manufacturing solar panels and transistors and thermal power and all of that are available cheaply or relatively cheaply. Anything else? Okay, come in next week for the damn talk.